Good morning, students. Today class we are going to discussing about the last unit. Now subject is Unit 5. It is a random process, spectral characteristics. In last unit, we had to discussing about the random process, temporal characteristics or time characteristics. In that unit, just we have to see that what is the fundamental definition of random process and how to able to define its first order and second order joint random process events and joint distribution events for a first order and second order. As well as they are also saying that the probability joint functions relating to random process, how they can be changing and what are the properties we are having, and how to consider the n number of events. N number of events, what is the formulas we are having, that we are saying in fourth unit. After that, we are also defining correlation. The correlation we have to classify into two types. One is a autocorrelation and second one is cross correlation. One is the autocorrelation and second one is the cross correlation. In that autocorrelation and cross correlation, we are also saying that the properties of autocorrelation and the properties of cross correlation. Once we have to complete those properties, we are able to simplify the problems by using the autocorrelation as well as cross correlation functions. And the last topics in that unit is the Gaussian random process. What is the definition of Gaussian random process and how to define its Gaussian density function in random process. It's a completely time-domain representation for that. And then we are also saying that the Poisson random process and its mean value and variance value. These are the topics we are discussing in fourth unit. In fifth unit, we are having the two parts. One part is related to completely the random process spectral characteristics. In this unit, we are having to discussing about random process frequency domain representation. In last session, we had to see the time domain representation, but in this section, we are seeing the frequency domain representation. It is a random process the random process we are representing in a frequency domain, and in this random process we are also discussing about the power density spectrum and its properties. What are the properties is having of the power density spectrum. Then we have to deriving the Wiener-Khinchin relation and its properties. Otherwise, we are also calling the relationship between power density spectrum and auto power density spectrum. It is the relation between power density spectrum and auto power density spectrum or autocorrelation power density spectrum. The another topic in this unit is already had to complete in the relation with autocorrelation is auto power density spectrum, and the second one is the cross, the relation between. Otherwise, we can able to find the cross density spectrum, and we are able to define the relation between the relation between power density spectrum and crash power density spectrum or crash correlation power density spectrum. In this topic, we are also seeing its properties. Its properties. This is the one part. Apart that, the second part is linear systems. Linear systems response. Linear systems response with random inputs. Random inputs. In this part, we are discussing that what is the system and what is the input and what is the output. Now, how to respond the system when not applying the mean value and when not applying the autocorrelation, how to respond the system when not applying the cross correlation function, what is the response of a system, we are discussing in this part. Then we are also discussing what is the classification of the systems in a random process. Here we are classifying those systems like low pass, high pass, band pass, and a narrow band and band stop. This classification we are discussing in this part. This is the structure of fifth unit. This is a complete structure of fifth unit, and I have to see some example problems in this unit. In this unit, the first topic is power density spectrum. Power density spectrum. First of all, what is the spectral characteristics? Generally, the random process we are representing with x of t. X of t. Here, the time domain we need to represent in frequency. Need to represent frequency and also obtain the function. And what are the function you have to consider? The function is also obtaining in a frequency domain. A is called the spectral characteristics of a random process x of t. Here we have to define the spectral characteristics of a random process x of t. For that, I have to consider random process x of t. It is representing in a frequency domain like x of omega. X of omega, and its function is also obtained in a frequency domain. Representation and the function obtained both are in frequency domain is called spectral characteristics. The spectral characteristics. The best example of spectral characteristics is Fourier transform. It is a Fourier transform. Suppose you need to take the Fourier transform of the Fourier. The best application of the frequency domain representation is Fourier transform. Here you need to consider the Fourier transform of x of t. X of t, it is represented with x of omega is equal to integral minus infinite to plus infinite x of t into e power minus j omega t into dt. This is a Fourier transform basic formula. Here, in this formula, the x of omega is representing the frequency domain representation of x of t. And this component is a exponential function. Now you can representing these components x of omega, it is a voltage density spectrum. Voltage density spectrum. The voltage density spectrum, we are measuring the units of volts for hertz. Volts for hertz. Volts is a magnitude, is a hertz for what are the parameters you have to consider in your horizontal axis. But in case of time domain, you have to take the time at horizontal axis. In case of frequency, we need to consider the frequency on horizontal axis. That's why I had to represent in the units is the words for hedges. Words for hedges. But here the voltage density spectrum, it not able to give the all values of the random process x of t. Here the voltage density spectrum is not giving the all values of random process x of t. That's why you can go for the power density spectrum. Why you can go for power density spectrum? The voltage density spectrum is not able to give the complete values of random process x of t. That's why I can go for the power density spectrum. Power density spectrum. The power density spectrum means we need to take the power. The power is with respect to frequency. You can represent in the power density spectrum, we can able to define each and every value of a random process x of t. Now we are saying that the derivation part of the spectral characteristics, the important parameter is power density spectrum. How to derive the power density spectrum by using this random process x of t. Now we are saying that the power density spectrum. For obtaining the power density spectrum derivation part, we need to consider some assumptions. First of all, we have to consider the random process x of t. Consider the random process x of t. In that, one sample function is small x of t. Here I am consider capital X of t is a random process. In this random process, one sample function is small x of t. For this small x of t, let x, small x, capital T of t is a one part on one sample function. The interval of minus t2 plus t, plus t. This is the interval I have to take in that. Now I have to represent the Fourier transform of a random process. The Fourier transform, before going to that, we have to represent the interval. The interval of small xt of t is equal to, is having a x of t. The interval is minus t2 plus t. 0 for remaining values. Now you can consider the Fourier transform. The Fourier transform of x of t. The Fourier transform of x of t, we are writing x of omega is equal to, the interval is minus t2 plus t. The portion you have to consider, the portion is x, otherwise you can take the small x, t of t e power minus j omega t into dt. The basic formula here. Now you can represent this interval in this range, that is integral minus t2 plus t x of t into e power minus j omega t into dt. This is just a Fourier transform representation for given random process within the interval of minus t2 plus t. Now you can represent its energy function. Now the random process x of t is having energy in the interval of minus t2 plus t. The interval we are representing here, the energy function we are writing with capital E of t. Is equal to, the interval is minus t2 plus t minus t2 plus t. Here you can writing x square of t into dt, x square of t into dt. Here you need to take the interval is t, xt, x suffix t. Then you have to substitute in the normal value. The normal value is e of t is equal, just you can write in the x term, that is integral minus t to plus t x of t sin the square into dt. This is the energy function. The energy function we are able to defining in a frequency domain. We are able to define in frequency domain. For this we are using Parseval theorem. Parseval theorem. According to that theorem, we have to representing any time domain function to its frequency domain. For that, I have to representing its energy function in a frequency domain, that is E of t is equal to 1 by 2 pi. That the interval is changing, is a minus infinite to plus infinite xt of omega, xt of omega modulus square into, in this function is a time domain, is a completely omega domain, is a t function. It is a t function is xt of omega square into d omega. Is a function representation by using the Parseval theorem. How to representing the energy function from time domain to frequency domain. Then we have to give that the average power. The average power is a P of t. P of t we are representing with P of t is equal to, in terms of their energy, is E of t divided by its complete time. Its complete time is 2t. Complete time is 2t, that is a minus t2 plus t. Now can apply this average power concept on random process x of t. Now we are applying, now we apply the average power on a random process, x of t. When not applying this average power on a random process, we need to take the expectation value. The notation of the power, when not applying this to random process, we are giving the pxx. Now you can writing the average power or a total average power, pxx is equal to limit t tends to infinite. What are the function we are having in this? You have to assign in the equation number 1 and equation number 2. From 1 and 2, just we have to substitute in the e function value here. Then you can writing is 1 by 2t into 1 by 2 pi integral minus infinite to plus infinite. Here we need to apply the expectation on xt of omega square. So expectation of xt of omega, the modulus square into d omega. Just I had to take the equation, but additionally I had to assigning the t values infinite, and one more thing is I had to apply the expectation. Now I had to adjust what are the values we are having in that equation. Those values I am arranging that for my convenient. I am writing the 1 by 2 pi limit t tends to, the limit also I have to move to inside. Now you can see here I had to move this limitation and 2t to we had to writing the inside of integration. Now I had to take that integral minus infinite to plus infinite limit t tends to infinite t tends to infinite the expectation of modulus xt of omega whole square by 2t by 2t into d omega into d omega. In this relation, what are the function is there inside the integration? That function we are calling the power density spectrum. Power density spectrum. The power density spectrum we are representing with del x x of omega. Del x x of omega. Here we have to represent the total average power. Total average power of a random process Pxx in terms of its power density spectrum is 1 by 2 pi integral minus infinite to plus infinite del xx of omega del xx of omega into d omega into d omega. This is the derivation part of the power spectral density. Power spectral density. Here, the del xx of omega, the del xx of omega is equal to this part is a limit t tends to infinite. T tends to infinite. The expectation of modulus xt of omega whole square by 2t by 2t. This function we are calling the power spectral density. It's calling a power spectral density. What we can do here, first of all, we can do this. We can derive the derivation part of power spectral density. Have to consider the random process x of t, the capital X of t, capital X of t. In that, I have to consider one sample. The one sample function I have to writing small x of t. In that sample also, I have taken the one interval. The interval value is I am writing the small xt suffix of t. Why I have to take the suffix t means it is lying the interval of minus t to plus t. Minus t to plus t. That one is I am representing like this. The xt of t, x suffix capital T of t is equal to x of t. This value is lying only the minus t to t interval. Except this interval, the value becomes 0. Then the fundamental representation of any function in a frequency domain is Fourier transform. Here I am to consider the Fourier transform for x of t. For that, I have to writing the Fourier transform representation of x of t is x of omega. I have to consider this interval. The interval function is x of t e power minus j omega t into dt. This is a basic formula for any function have to represent in Fourier transform. Then we have to represent this quantity with its equal value is x of t. Why I have to write in x of t? Within this interval, this function is x of t. That's why I have to replacing the x suffix capital T of t with small x of t. Now, I need to take the energy function of random process x of t. The energy function we are representing with capital E. For time domain, we have to take the E of t. E of t, that is minus t to t, is xt square of t into dt. Then we have to replacing the xt of t with x of t, that is x square of t into dt. But I want to that energy function in frequency domain. For that, I have to use the Parseval theorem. Parseval theorem is saying that any function you have to represent their frequency domain. According to that, the energy function is 1 by 2 pi. You have to represent in omega domain. The omega is minus infinite to plus infinite. The xt of omega square into d omega. Only the function is change into omega, and now to take in the inverse is 1 by 2 pi. Here you can consider the average power. The average power you can obtaining the energy is dividing with its complete duration. The energy is lying between minus t to plus t. Here you can take in this interval, can writing its complete duration is higher limit minus lower limit. Higher limit minus lower limit, there is a totally 2t. That's I had to division with this entire energy value. Then I had to apply this average power concept on a random process. I had to take the expectation. What are the average power we had to consider already on the random process? We had to take the expectation and we had to apply the limit is infinite. That thing is I had to do in this equation. Is the limit tends to infinite and I had to take the expectation on that particular equation. Then I had to moving this, what are the variable parameters is there, those parameters I had to moving to inside the integration. The remaining constants I am writing outside of the integration. For that 1 by 2 pi is a constant, that's why I had to keep this value is outside of integration, and remaining values I had to move to inside the integration. Those are limited tends to infinite, the expectation of xt of omega whole square by 2t. This function we are calling the power spectral density spectrum or power density spectrum. The power density spectrum we have to represent with del. So del of xx of del suffix x xx of omega. That one is we are representing in terms of the power. Power is representing their power density spectrum is this equation. The equivalent value you can represent with its equivalent notation. The notation value is this one. This function we are calling the power density spectrum. This is the derivation part. How to doing for power density spectrum derivation. This is the power density spectrum derivation part. Now we are saying that the properties of power spectral density or power density spectrum. We are representing this. We can also calling it is a power spectral density. That one is where shortest notation is PSD. PSD. The properties of this one is the first property, the zero frequency, the power spectral density of void sense stationary random process. Stationary random process is equal to the total area under the graph of autocorrelation function. Graph of autocorrelation function. We can having these properties is a completely Wiener-Khinchin relation. Wiener-Khinchin relation. According to Wiener-Khinchin relation, the power spectral density and autocorrelation function both are Fourier transform pairs. Both are Fourier transform pairs. According to that condition only, we have to take in the relation is del xs of omega is equal to minus infinite to plus infinite is rxs of tau into e power minus j omega tau into d tau. In this formula, we have to make the frequency value 0. That is omega is equal to 0. Then rx is the del xs of 0 is equal to integral minus infinite to plus infinite rxs of tau, the e power 0. E power 0 means is 1 is d tau. This statement is saying in that first property, the zero frequency, the power spectral density of a WSS of a random process is equal to the total area under the graph of autocorrelation function. It is representing the total area of autocorrelation function. This is the first property. Coming to the second one. The second property is the mean square value. The mean square value of void sense stationary random process equal to, the random process is equal to the area under the graph of power spectral density. Power spectral density. Already we are saying that Wiener-Khinchin relation. According to Wiener-Khinchin relation, the del excess of omega and RHS of tau both are Fourier transform pairs. Here you can see that you can obtain this value, you can take in the inverse Fourier transform. There is 1 by 2 pi integral minus infinite to plus infinite. Have to moving this integration to this side, the del excess of omega, and the negative sign will be changing to positive sign, like e power j omega tau, and tau is represented with omega. In this relation, what he is saying that the mean square value of WSS for random process is equal to the area under the graph of the power spectral density. Power spectral density. In this relation, you have to keep the tau value is 0. Tau value is 0. The tau is equal to 0. Tau is equal to 0. You can writing R x of 0 is equal to 1 by 2 pi integral minus infinite to plus infinite del xx of omega e power 0 means the 1 into d omega. But here RHS of 0 in autocorrelation function, the RHS of 0 is equivalent to its mean square value. The property is RHS of 0 is equal to expectation of x square of t is a relation, is a hang-on property of autocorrelation. According to that, you can writing the expectation of x square of t is equal to 1 by 2 pi integral minus infinite to plus infinite is a del x of omega into d omega. This is the statement he is saying in this property. Now coming to the third one. The third one is the power spectral density of WSS random process is always non-negative value. Non-negative value. Here already we are seeing this value. This value is always is greater than or equal to 0 for all values of omega. Now you can see the fourth property. The del excess of omega is a real function. Is a real function. Since why you can call it as a real function, the modulus of xt of omega is also be real function. The basic parameter of a random process in frequency domain representation is a real function. That's why the value obtained of power spectral density is also be real function. Coming to the next property, that one is the power spectral density of derivative of random process x of t, derivative of random process x of t, that is d by dt of x of t is omega square times of the power spectral density of random process. Power spectral density of random process. How to write in that the del excess of omega is equal to is a omega square. It is a omega square times of its power spectral density. Coming to the last property. The last property is the power spectral density of a real valued function. Real valued function of a random process, always an even function. Always an even function of frequency. We can prove this property. We have to consider the del excess of omega. Del excess of omega formula in terms of their autocorrelation. In this formula, first case we had to choose omega is equal to minus omega. Where omega is there, we had to keep the minus omega. That's why I had to substitute the minus omega in this equation. Already here I have the minus sign, the minus into minus, the plus. The remaining equation as it is. And then we are also consider one more assumption. That one is the tau is equal to minus tau. Tau is equal to minus tau. In this case, we have to replace where tau is there, have to keep minus tau. We have to substitute like this. We have to form in this equation. Then we are having one property according to the even function property of autocorrelation. That is Rxs of tau is equal to Rxs of minus tau. By using this property, you have to replacing the Rxs of minus tau with Rxs of plus tau. This quantity is equivalent to the normal power spectral density. Therefore, I have to consider the negative sign of a omega is equivalent to its positive sign of its power spectral density. These are the properties we are having under power spectral density.